If we have two equal but opposite charges side by side, how does their field behave far away? And how fast does the electric potential drop off compared to just a single charge by itself? In this video, I'll teach you how to find the electric potential at a point P that's caused by a dipole. A dipole is two charges, positive and negative, separated by a distance of L. And a dipole is one of the most important configurations in all of physics, biology, and chemistry. It's two equal and opposite charges separated by a small distance. That's all. The core assumption is this. We will focus on the potential far away from the dipole, meaning the distance is much bigger than the distance between them. Here's a step-by-step derivation, and I recommend you go through this because deriving formulas makes them stick in your head and make you understand the entire concept much more intuitively. And the formula that we're trying to derive is this. B equals K QL cosine over R squared. That's our goal. We're going to set it up in the corner so that we know what we're looking for. Let's say point P is a certain amount of distance. Let's say distance R from the dipole. With this being our dipole, this is the distance between the charges, and this is the distance from our point to the dipole. And by the way, this looks like an equal triangle. It doesn't matter. It could look like this. We're trying to derive the formula. What I'm saying is this configuration is irrelevant for this derivation. The distance from the positive charge to P is R. The distance from negative charge is R plus the change in R, where change in R is equal to length times cosine. Why? Because this distance, well, we have to take the x component. Fine, so cosine. I'm not going to go into it too much because, of course, derivations are often very math heavy. If you're not fully following along, it's all right. But what this says is that the total potential is equal, so right, V for potential is equal to KQ over R, which is the potential at point 1. And this is the potential for charge, the positive charge, minus the negative charge's potential, just this. And this is the total amount of potential in our dipole. You can factor out KQ. You get KQ 1 over R minus 1 over R plus L cosine. And we just expanded this here. Now apply the Taylor approximation. This is why I say that the math is getting heavy. When you apply the Taylor approximation, which you don't have to know what it is, since L is smaller than R, then we get V is roughly KQ length cosine divided by R squared. This is our final expression. This is what we derived. This is the potential of a dipole with a far electric field. What this tells us is it drops off like 1 over R squared. It's inverse square law again, just like Earth's gravity. So if you move 2 times as far, it drops off by 1 over 4. If you move 3 times as far, it drops off by 1 over 9. Not linear. It's explosive and it has angular dependence. It does matter with the angle here. That's why cosine is in here, which means that the alignment is at its maximum only when the angle is 0 degrees. What is a dipole moment? We define P equals charge times length as a dipole moment. And a dipole moment, QL, is in our formula. Look, QL. So we can rewrite our formula as V equals K, dipole moment, cosine over R squared. This is going to be put on the cheat sheet in the description, but here are the units of a dipole moment. It's coulomb meters, and it's often expressed in dBys, and 1 dBy is equal to 3.33 times 10 to the power of negative 30 coulomb meters. These are the units of a dipole moment. And here's the key comparison. A point charge drops off 1 over R. It's linear. Drops off linearly with distance. But a dipole, which remember is this famous configuration, a dipole drops off exponentially. Inverse square law. And dipoles vanish faster at a distance. They self-cancel from very far away. So if you back away from a dipole, the plus and the minus start to cancel, but the separation still matters. That's what the dipole moment captures. You'll use this idea later on for torque in the dipole in a field, or even the polarization of materials. This was a pretty math-heavy video. Make sure your math skills are sharp.